So we move on with the second talk of this afternoon session, which is by Alessia Pasquazi, I hope I said it right, University of Sussex, and it's about quantum technology. So you have heard already in the very first talk that you can take the approach that, you know, we don't understand quantum mechanics, but, you know, it seems to work, so we know how to prepare quantum systems, and we can generate superposition and entanglement, and we can actually try to make use of this in form of technological applications. And I guess you know that there's quite a lot of investment in this country and also on the European level to look what is actually in this quantum technology. So what kind of devices can we make which are based on quantum mechanical features? So I hand over to you.
Thank you very much for the kind introduction, and I want to thank the organizer for having me here today. It has been a really great conference, a great day with a lot of different perspectives. So I think that my role is to try to bring everything to our everyday life, and we see if we make it. So I have been asked from Joanna to make a survey of all the key invention and technologies from the beginning of quantum mechanics. Is a little bit a daunting, let's say, process. What I have done is that I've asked some help to Google, because Google knows everything, right? So I asked some help to Google, and I've searched for quantum. And what is impressive is that if you search for quantum, you get something like almost 200 million of hits. So it's a huge number. If you compare it with what you get when you search for beer, no, I don't have to say why I was searching for beer while preparing this talk, but in any case, if you search for beer, you get 700 million of hits. So what I can tell you is that Google, in any case, does a pretty good job with the beer. So I suggest you good beers, good places where to find it. If you want to buy something quantum, so to go to our everyday life, is what you get. So you have a quantum golf umbrella, a quantum thermostatic mixer shower valve, a quantum aluminum cabinet, and dishwasher tablets. So probably this was not the organizer were expecting. So we try to move on and go on with history a little bit. So we heard a lot of interesting things today about quantum physics. So today I have to talk about quantum technology. And the first thing that I have to make clear is that clearly the time scale of these two things are different. Because the task of technology is to take the things that we understand in physics and to use them properly to create new stuff, right? So the time where we are today, we call it the information technology era, has been the result of the first quantum technology revolution. And the first quantum technology revolution used all the concept of wave-particle duality that we have discussed at the beginning of this morning, okay? All the things about superposition, entanglement are still not that much used in the things that we have today. And let's say that those are expected to ignite what we call the second quantum technology revolution that hopefully will happen very soon, and we will see a little bit of things about it at the end. So I will go quite quickly on this because we have seen a lot of stuff, but the experiment that ignites most of the first quantum technology revolution is the photoelectric effect, and I go very quickly so you can see from my slide the perspective of an engineer, because my work is done by bolts and lines. So, and I explain everything with that. But in any case, this is a great experiment that Leonard and Hertz were doing at the end of the Victorian era. So what they were trying to do is that they were trying to convert light into current. Now, this is, if you think, it's a mind-blowing thing. So we have a bulb of light, we put close to 2 pieces of metal, and we close the circuit. Incredible stuff. Now, the things that, however, was puzzling these people was that when they were changing the color of the light, like using very low frequency, this thing was not working. No matter how bright was the bulb that they were using, this was never working. When they were using instead high-frequency light, something like a blue light, it was working even with little bit of light. This was puzzling. The puzzle was solved by Albert Einstein at the beginning of the 20th century, and Robert Millikan did the experiment. You see, this is the perspective of an experimentalist. I always put the guy that performed the actual experiment with that. But Einstein understood that the nature of light was quantized, so that all these waves that were arriving there were actually containing particles with a little bit of energy, so a quantum of energy, discrete, and this quantum of energy was proportional to its frequency. So what was happening eventually is that when you were using a blue light, you had big photons, so now we can call it with their name that we use nowadays, with a lot of energy. So every time that this photon was hitting the electron, was giving it a lot of energy, was jumping up and was closing the circuit. Now, with the red light instead, what was happening? No matter how many photons you were using, you were hitting a lot of electrons, but they were doing just little jumps. Okay, nothing big enough to close the circuit, and so it was not working. Now, brilliant. So, puzzle solved. This is the photoelectric effect, and this is the, let's say, the seed that ignites our understanding that wave and particles can be sometimes the same thing. Now, let's try to make now an experiment, because we have to see how this is impacting our everyday life. What is happening if we go home today, we sit on our sofa, and magically everything that works on the photoelectric effect disappears? Let's see. Okay, so this is a joke, and this is an alternative technology that you could use. So maybe I spent too much time in front of the TV, but in any case, the remote is one of the things that always remind me of the photoelectric effect, because you have something in your hand that has a source of light, very efficient, also another results of quantum technology, but in any case, you point it to the TV. When you point it to the TV, you have your photons that travels, then hit your detector, and then you have an electron that jumps, close the circuit, and allows you to change the channel. So now, forgetting about the joke, in any case, the photoelectric effect is at the basis of all the things that we use in these days for measuring light. So if you want to measure light, we use the photoelectric effect. And other things that we do, if you want to convert light in electricity, we use the photoelectric effect. So all the photovoltaics are based on this concept. And let's say, again, this understanding that the photons is a wave and is a particle ignite the first quantum revolution. We have seen that the same thing is real, is true. Now, reality is true, I'm sorry, this is not actually my domain, but in any case. So it's true also for electrons, thanks to de Broglie. And then from the understanding that electrons can behave as waves, we had all the development of semiconductor technology. Now, I will not have the time to really enter into the details of how everything works, but you know that basically all the things, many of the things that you have are based on electrical, on integrated circuit. And we can be so efficient in creating such good integrated circuit because we know precisely how to redirect the electrons both on space but also on energy. So we can, and this is happening because we understand how they work as waves. Other things that work as both particle and waves are magnetic nuclei, for instance, in medical imaging like MRI, magnetic resonance imaging. In this case, here you have a nucleus of an atom that is under a magnetic field, and it resonates. And we can detect that radiation, so we can make images with that. So how important is in our society the possibility to see the things in our body? So how many lives we save thanks to that? So again, not much time for that. I will spend a little bit more of time to discuss about laser, a little bit because it's it's what I do for living. I'm a photonic girl, so I like light. I like light a lot, but also because lasers are an excellent examples of a kind of technology that created a lot of fallout technologies. So let's start then, before starting to see how they work, So how they are made. Let's try to understand why they are important, why we do a lot of things with laser, why the laser light is so special. So technically we call it a coherent light. So if we watch this, this is a laser show. So if you watch this, we see that laser beams are almost propagating as ray light. All the energy is really, really well concentrated. And another thing that is important is that the color is just a single color. So those are the property of a coherent light. Single color, and thanks to the fact that we have a single color, we can put a lot of energy in that and allowing it to just propagate like this. Why this is important? This is important because we can concentrate a lot of energy in small, small volumes. And so lasers are highly, highly used in manufacturing. We use them for cutting metals. We don't use basically other things anymore. We cut things thanks to laser. And another example that I have in here of a fallout technology of the laser is this little Tour Eiffel. Now, this is something that, we printed in our lab. We have a 3D printer that costs £2,000. So it's really something that you can buy, quite easily. But what is interesting is that this thing is done thanks to a laser, a UV laser that moves and point by point changes this condition of a polymer, so it makes the polymer to change state. And we can achieve accuracy of the order of the microns. So micrometric precision of something that you can draw on your PC and then printed it out. And this is thanks to the fact that we can have laser that we can control in terms of power and in terms of colors. Other examples are, LASIK surgery, something like this is LASIK kind of surgery. So there are people that can get glasses directly imprinted on their eye, depending on their condition. And we are trusting it because lasers are extremely accurate. So now, I hope that everything is going far so far. But I would like to make clear an important point. So when we make light interact with material, it's very important that we control the color. For doing that, I've brought here a very, let's say, an example of another very popular technology that is laser hair removal. Let's think about laser hair removal works. Okay, so if you want to remove your hair, you can take an infrared laser, you point it to your skin. Then what is happening? It's happening that your skin is transparent to this light. So the laser penetrates inside your skin, reaches the root of your hair, that absorbs the light and is killed. Okay? Now let's imagine that instead of doing this thing with an infrared light, that your skin is very transparent to, we do it with a UV light. So what is happening when you put your skin under the UV? You get tan, right? So best case scenario, usually you get burned. So this thing will never work if we were not able to precisely control the color of the light. So that is why lasers are so cool, let's say. We can do a lot of things with that. Let's see how lasers are done then, how we can do it from a physics point of view. Okay, yeah, okay. So again, lasers are done thanks to the properties, thanks to, let's say, a clever engineering of the property of matter. Here we have, let's say that we have an atom with some electrons. We have these electrons that can stay, we select just two energy states, okay? The electron can stay down or can stay up. Now, let's say that I am very, very, very good and I'm able to put all the electrons in the upper state. So it took almost 15 years to these guys to do that. So just to do this little bit. So this was not an easy thing. But let's say that I make it. So when I have my electron up here, if I take a photon that resonates exactly with this energy here, so it resonates with the electron goes down. Going down, it releases energy, and it releases an energy in the form of a photon that is exactly locked to the photon that you have in here. We call this stimulated emission, And if you repeat this process in cascade, at the end you get a coherent beam. So this is how this thing works, and is the results of the work from many people. And in the end, the experimental demonstration was of Theodore Maiman in the 60s. Now, how can I change the color of the laser? I have to act on these two energy here. So what can I do? I mean, the first thing that I can do is to go and see what nature gave to us and look into the periodical table. So we have many lasers with a lot of different colors, something like ruby that is in red. This is a crystal of neodymium YAG. It produces light in the near infrared. After some time, people started to being able to put this kind of important emotes inside the glasses, to dope glasses. And then from that, we started with things, something like fiber laser, that have been extremely important for the technology that we have every day. This is the University of Southampton has really pioneered this kind of technology. What else can I do? I could try, for instance, also to create new atoms. Now, this is a little bit overselling, but what people have been able to do is that they have been able to put this electronic state more or less what they want, where they wanted. And they had to use a little bit of the new physics for that. So we are entering at the beginning of the second quantum technology revolution. So as promised, I've brought you I've brought you to the information technology era. So all this background of the laser, another huge fallout of this is that today we have the internet and all the communication that we use. And this is thanks to the development of fiber technology and communication over fiber technology that is empowered by laser. Now, there is a very important consideration that we have to do. So the amount of data that we exchange every day, it's huge, and it dissipates a lot of energy. Now, we can communicate so much just thanks to the fact that the fiber are an extremely low consumption material, so they basically don't absorb any energy. So this technology would never be possible with cables of telephone cables, you know, this kind of stuff, because the energy dissipation would have been too much. Okay, so if we are fine with that, I would like to do now a little step forward and try to see what we can expect next. So for doing this, I have to talk about another important player, especially in communication, that is time. So for communicate with different places, so when you are chatting with someone that can stay in another continent, you are sending a message out. Now, it is important that this message is reconstructed properly, so we have to time it properly. So the best clock that we have nowadays are the atomic clock. So you have to connect all the things. The best way that we have to keep time is thanks to atomic clock, and the atomic clocks are also, let's say, somehow will help me to bring you to what we can expect next. So I will go quickly on to summarize how they work. So the first thing to do is to say is that the atomic clocks, the first atomic clock was built in here in the UK, and the NPL by Jack Parry and Louis Hessen. They built up a cesium-based atomic clock. So now, how an atomic clock works? An atomic clock works more or less like a normal clock. So a normal clock, let's say an old-fashioned clock, like the pendulum clock, has a reference that is your pendulum that moves and you can count 1, 2, 3, 4. Every tick you count, then you need to have a reference and a counter. An atomic clock works in a very similar manner. So you have two states for your electron. You put these two states in a superposition with an electromagnetic wave. When this superposition is maximum, again, we have to play a bit with probability, but when this probability is maximum, we know that this electromagnetic wave resonates with that, and we can count the electromagnetic wave. This is what they have done the first time, so with cesium. Now, the beauty of the atom is that if I build up an atomic clock by myself with cesium, and you build up another one by yourself, we can be sure that the oscillation of your clock and my clock will be exactly the same. the cesium oscillates around 9 gigahertz and something. So that allows people to move the definition of the second from the astronomical time, because before we were using that, before we were looking at the sun and define the second with that, to the atomic time. So this has happened in the 50s. And then we have a lot of development by, those are all Nobel Prizes. I will go fast on this thing, that in any case improve the way of doing the counter and the reference. And thanks to them, now we have atomic clocks with accuracy of 10 to the minus 18. So now your atomic clock can be upgraded to 10 to the minus 18. Now you can ask yourself, first of all, I don't have an atomic clock. Second, I mean, personally, I'm late in any case, so I don't need to be that accurate, right? So the second is, for me, in my case, is totally sure. But you actually have an atomic clock. So we are in a moment where we are all sharing atomic clocks. Atomic clocks are in the sky, on satellites, and thanks to them, we can have our GPS that is working. Now, I mean, I don't know about you, but personally myself, without the GPS, I'm lost. So I came here with a map and with these little balls that were directing me in the place. But what is most important is that all the things that we are moving today, so imagine about the shipping on trucks, on ships, and all this kind of moving of things, all people are navigating thanks to the GPS. Now, GPS is extremely vulnerable in some cases. So when the signal is lost, stuff is lost because people don't know how to find the route. So especially for the ship, this is particularly important. So what we are asking ourselves, and we are trying to do a jump to the future then, is can we put an atomic clock directly on your mobile, on your GPS, so that you can find the way without having to look into the sky. So this is part of the technologies that are going to come. Portable atomic clock, quantum communication, quantum sensing, and quantum computers are all things that we are going to build, let's say, based on superposition and entanglement. There is a huge effort all around the world to do this. This is a picture that I've taken from the Economist and show you what is the investment of several countries in quantum technologies to bring this thing to industry. In the UK, we have the UK Quantum Technology Program by the EPSRC. So if I have a little bit of time, I will give a perspective, on this. And okay, so 4 national hubs to translate lab research into industry, and Birmingham, Glasgow, York, and Oxford. I work with Birmingham guys, so I will give you a little bit more large perspective on what we are doing with them, and summarize the work also of our colleagues all around the UK. So Birmingham Quantum Hub, trying to build up, on the route for building up a quantum sensor, gravity sensor, magnetic sensor, and gyroscope. Especially the gravity sensor here will work with an accurate reference of time, because basically to measure the gravity, I can measure the gravity here, the gravity there, but I need to know precisely the time where I'm measuring. So what I'm working to personally myself is to build up a reference, an optical reference that for the moment is something big like that. We are trying to put it in a desk. So this is the leader of the hub in Birmingham, Kai Bongs, and he is working on atomic reference in strontium, and this is one of the ion traps of our colleagues, Matthias Keller in Sussex, that is also miniaturizing these references. So we are trying to arrive at the shoebox, let's say, and as you see, this is one of the first references, industrial references by E2V, that is an extremely think-forward company. That has, this is really recent results. When we will have a portable atomic clock, we will be able to do a lot of things. So navigation, we discussed. So if we are able to get a better GPS also in the sky, we will be able to look at and to profile the Earth much more accurately. And we could do all things, something like precision agriculture, really try to understand much better what is happening on the large scale. Having gravity sensor means that I will be able to look what is underneath my feet. Then when I dig a hole, because I have to do some kind of work, I will be sure that I don't have a pipe, and so I can dig my hole safely. You don't know how much money we are just wasting because we are digging hole in the wrong places. Another thing, yeah, it's reality. So another thing that is important is in the stock market. Stock market can have exchange that go really fast on the order of the microseconds, and sometimes the only way that we have to reconstruct, usually unfortunately is a crisis, is to put all the transaction in order. So if we can time tag them, then we will solve a lot of problems. So those are all things that will be possible thanks to the next generation of atomic clocks. Other stuff that is happening in the Birmingham Quantum Hub is to have better, more accurate magnetic sensors. So we have seen before the MRI, right? So it's a quantum technology that helps a lot of life. This is the new generation that will be smaller and, most importantly, much more accurate. And this is the work of the group of Tim Frommold and Peter Kruger in Nottingham. Now Peter Kruger is with us in Sussex. Other things, so let's give a look to the other hub. What are other people doing? Quantique Glasgow, it's led by Miles Paget. They are working on quantum imaging, specifically on on single pixel camera. Now, this is an extremely, let's say, even puzzling thing that they are doing. So they are basically building up a system where you can make an image of an object that is very far away, even in the fog, with entangled light, okay? And they are doing this thing without using a camera that is looking at the object. So the idea is to use the property of coherence and correlation of light beams. Let's imagine that I do have these two beams of light. They are pattern of light, and they are entangled. So we have heard a lot about that today, right? So you know that if something happens to this pattern, I will see it here because it changed states and changed states also here. So let's say that I want to make an image very far away. So I send this pattern to there, and then I have a camera just here with me, and I'm imaging my other pattern. Okay, if I keep this thing if I keep doing this thing for many patterns of light, I need just a little bit measurement of power from you, but not a camera, so I need just a little sensor. With this thing, what is mind puzzling is that I will see appearing on my camera here the image of the object directly. This is called ghost interference. It's one of the weird things of quantum mechanics that actually works. This is an example of, again, this is a work of Miles Paget, a recent one. The nice thing is that they can see objects behind screens with that. So if you have a screen, this is what you take with a normal camera, and this is what you take with this process. So you actually can see things, because you are working on correlation. The other beauty of this process is that you can make this thing work even with classical beams. So we can probably relax a little bit ourselves about the weirdness of quantum mechanics, but you have to imprint a good correlation between the two beams. So correlation is the key. And also they are going to the market very soon. So really this is something that is arriving to industry. Now I do a little bit of advertisement now for my lab. This is my lab in Sussex, the Emergent Photonics Lab. And we have been, actually Marco Peccianti, that is working with me, have been awarded by the European Research Council to do something similar with a kind of wave that are called terahertz wave. Now, probably you have not heard much about them, but if you have been to the airport, and I don't know, any of you have done the body scan, did you happen? So this thing works with terahertz wave, because they can pass the clothes and you can see all the metal objects. So terahertz is quite an interesting kind of electromagnetic wave. The other thing that terahertz can do is that it can look at molecules. So what we are building up, and we will see what is happening in the next 5 years, we are trying to build up a microscope for molecules that works at terahertz but can be used with an optical camera. So we'll see where we are in a little bit of time, but okay. So York, quantum hub for communication, 5 minutes. So I will go fast. This is the thing that works with the Einstein-Podolsky paradox, the APD paradox. So they are building up a system that is secure for quantum communication. Now, one of the other beauty of quantum mechanics is the so-called non-cloning theorem. It works again on the concept of having two entangled beams, for instance, of two entangled photons. So let's say that I want, so first of all, I have to tell you how secure communication works. So secure communication works like that. Let's imagine that you want to send a secret message to someone that usually it contains probably the data of your credit card, but you want to send it out. You put your message in a box. You close the box with a key, then you can ship the box wherever you want if you have the key with you, but you need to find a very secret channel to give this key to your friend eventually, and when he gets the box, he can open it, right? So this is how communication works right now. So the critical thing is to then ship somehow this key for encrypting the message. So the beauty of the non-cloning theorem is saying that if I have a source of entangled photon, I keep one with me, I send one to you. And I keep this doing with many, many of them. So eventually I will have a series of photons myself and a series of photons for you. That is, we know it, so if you know yours, you know mine. So I have a key and you have a key, and I have a key that I can use. The beauty of this thing is that from the statistics of this photon, I can be 100% sure that there is no one that was there stealing my photon, taking the same one and putting back to the channel, because I can see it from the statistics. So this is a theorem. So we are pretty sure about that. Pretty sure about that. But in any case, so this is important then, if you think of all that. This is just a reminder of what happened last month here around. I don't know if you have been to the doctor, but in any case, a lot of cyber attacks are happening almost every day. Yesterday there was one to Al Jazeera, I think. They also have been cyber attacked. So we are very vulnerable to that. We need this kind of channel. So the group of Tim Spillane in York is building up the first quantum secure network here in the south of the UK. So that is something again that is happening. It will be a secure network. Now, to conclude, that I'm really done, just a little bit of background on what is happening locally here in Oxford. And KIT is the hub for quantum information technology led by Ian Worsley. Many things happening. One of them is the quantum computer. Now, I will try to say everything in just 1 minute of quantum computer, but okay, so we know that a computer works on many bits, yeah, right? So you need them to say a lot of things, you need many bits, you need a large memory to put all the things. Now, if you have a particle that is in a superpositional state, so you can put it in two states, like dead and alive cat and all these kind of things. So it can be up and can be down. But if you can increase the number of superpositional states, you can put again a lot of information just in a single particle, and that is extremely efficient from a computational point of view. Another strength of the quantum computer is that it can do extremely efficiently algorithm that like factorization of prime numbers and random number generation that may seem a little bit abstract, but actually are all the algorithms that are important for cracking the secure communication. So it is extremely important that to have the control of this kind of computer, and things are happening again. This is an example of one very compact quantum secure network by the group of Iris Choi, and this is a news instead of from our Winnie Hensinger here in Sussex that developed the first plan of a quantum computer based on ion traps. With this, I'm really done. Okay, so just a little bit of advertisement for our Quantum Technology Center in Sussex. Thank you very much for your attention.
Yeah, thanks a lot. So let's open for questions.
Thank you for that talk. We heard a lot earlier about, well, this is only instrumentalism. And what your talk is showing is, boy, what instrumentalism. Can you think of any place where advances in interpretation would actually help your technology, or is it that the instrumentalism is just so good we don't need interpretation? You can just go away and do that separately.
Now, this is a very good question, and I don't know if I actually have the answer. So, I mean, from the perspective of an engineer, I usually believe, right, to a model. So I'm really well aware that the model has a boundary, and so as long as I stay inside this boundary, I'm somehow safe. Now, the things that needs to happen is that I cross the boundary and I go out from that, and that is what usually is happening in terms of physics and philosophy. So, from my perspective, what I do expect probably is, going back to this picture here, would be to have the third wave of a third wave happening here. So when you will give me the explanation of how other things happen, so from the engineering perspective, I should be able to do a lot of other things. But from my perspective, I need to be sure that the physics is working. Yeah.
Probably do it in my voice, that's all right, yeah. I heard something on a podcast the other day, Dreadful Things podcasts. Good, very good, very informative. It was about optics, about lenses. Do you know any work anyone's doing some solid-state lenses instead of using glass? And I don't know if that falls into a similar technology.
Okay, so this actually goes to somehow the age of Fresnel. Now we have much better accuracy, but we have heard about the interference, and how people, well, Poisson was not that keen in this interpretation. So Fresnel at the time was doing lenses for lighthouses. The Fresnel lens for the lighthouses. So, and what he was doing was he was able to control. So instead of having a big lens, so he was cutting little bit pieces of lenses down and making it flat. So what we can do with a lot of technologies, something like liquid crystal and all these kind of things, we can control the refractive index more or less in the same way that Fresnel was doing, in a little bit more, for instance, a little bit more efficient way. There are frequency ranges, like, I mean, the terahertz is one of them, where doing this job is extremely difficult. But we have many technologies. Depending on the colors, we can perform better or worse. Thank you. Yeah, thanks.
Do you know if much work is going on in quantum technologies applicable to renewable or sustainable energies? I know it's not in your field.
I mean, there are things especially in photonics. That is, let's say, photonics. That's my field of research, and sometimes it's more related to the first quantum technology revolution. So we are based more on the concept of wave-particle dualities. But there is a lot of things going on, especially in trying way of transport energy better into light, or trying ways of converting the energy of the solar light in a much more efficient way. So that's one of the problems that I mean we are facing with solar light is that silicon, that is the material that we use for the solar panel, because it's extremely cheap technology. That's the reason why we're using it. It's transparent for most of the solar light. So a big problem is to find a material that is cheap, can be engineered for doing a solar panel, but it can also, let's say, acquire all this infrared light that the silicon just let pass and is completely lost. So that is probably one of the challenges at the moment.
Okay, yeah, there's one more question here.
Just given that this is a conference on quantum reality, so I often sort of hear the stereotype that experimentalists are so busy doing their absolutely wonderful experiments and building technologies that they don't really care about sort of interpreting the theory and worrying about reality. That's left for sort of philosophers or theorists. But as an experimentalist yourself, I wondered if you felt that was true, or if you had any thoughts yourself on sort of interpreting the reality of the quantum state.
I mean, myself actually every time. So, especially this happens, especially when I teach the lab to the youngest undergraduate. So I'm always amazed of the fact that the pendulum experiment always works. So it's a personal feeling that I do have, that the nature is strongly coherent. So and every time I have my guys doing the experiment of the pendulum always work. The experiment of the photoelectric effect and all these things, let's say the simple one, they are always working fine. And yeah, it's a thing that strikes me usually, a lot, of seeing that there is this repeatability continuous of the experiment. Yeah.
Okay, so there's another question over there. So I'm the chair. I should be neutral. I should not say anything, but I want to make it. The case that there are a lot of experiments which, are interested in the foundations of physics and actually looking into those questions. So, for instance, preparing superpositions which are very large and, just try to see where it ends, if there is an end, look at the coherence mechanism. So there's quite some effort.
It's always been a source of mild amusement to me that the kinds of vulnerabilities that we've seen in recent hacking episodes are not so much in the way that messages are encrypted. The encryption seems pretty secure. It's other vulnerabilities in the system that the hackers are going for. But of course, with the rise of quantum computing, then the kind of encryption algorithms that we're using today for banking transactions and other things do become very vulnerable, which is why I'm sure you said that we need to keep control over who's developing quantum computers. Do you have any sense for how quickly we will have quantum encryption systems that were able to offset the power of quantum computers to decode messages that are currently encrypted?
This is a very debated topic. It's a very debated topic. So if I listen to my friend Winnie Hensinger, that is the guy that is working in quantum computing at Sussex, he's always promising me that this quantum computer is coming out, will coming out next month. So at the moment, so I think that likely. People, especially people from the STL, they have the Department of the Defense and Science and Technology Lab. They have a perspective of this thing, and so we expect that this stuff probably will happen in 10, 20 years. This is what we are really thinking to go there. What will happen much more quickly will be probably having your own atomic clock with you. But quantum computer are a little bit more far into the future. Even if there is the D-Wave from Google, and everyone is really wondering. Yeah.
Okay, there's one more question there.
Yeah, with quantum technology, does it lend itself to improve batteries for cars?
Batteries, sorry?
Batteries for cars.
Wow, I don't know. I mean, this is honestly,
good,
honestly, I don't know. I mean, I'm sure that there is a lot of work from the chemistry community from this, and I mean, from this the roadmap that we have in here. We are not targeting them from these topics, but yeah, I'm sure that there is a lot of work going on for having small and compact batteries, also for the cars, I think. Yeah.
Okay. So you have a question?
Yeah. Hi. Thank you for a great talk. I don't know about batteries in the cars, but if you were to play a bit of a futurist and think of an absolutely transformational technology that is going to be enabled by some of the things, some of the research and experiments that you're currently carrying out, what would it be? And I also have another question, which is maybe a little bit flippant, but I am still hoping for teleportation. I know that quantum physics absolutely forbids that, but what is your view on that, and is there any hope?
Yeah. I mean, on teleportation, I don't answer. So quantum physics, apparently we don't. I still have my husband that is watching continuously Star Trek, and so yeah, we do see all this teleportation really often. So transformative technologies. So from an optics point of view, we have many things that we would like to do in the real future. So in the near future, most of it is to go and try to shrink down a lot of the system that you see around. So for instance, another a great challenge for the photonic community will be to build up a sort of internet completely integrated, so that you could really do a lot of communication, a lot of exchange, energy efficient, directly on the microchip. That would be probably completely transformative in the sense that will give a lot of computational power together with the quantum computing. So those are things that are working together. From my perspective, for sure, I do see in expanding the power of computation one of the most transformative things that may happen. Yeah.
Okay. Yep. Question?
I just wanted to emphasize this relationship between experimental and the notion of fundamentals in quantum mechanics is done extensively at CERN, for example. I mean, we do, 600 million experiments per second to test a quantum mechanical effect. So, it is heavily well tested, and we do care about reality substantially as well.
Yeah, I mean, I think there are things like the standard model that are pretty strong, right? So it seems that it stays and it works fine. Yeah.
Okay, so do we have more questions at this point? If that's not the case, then let's thank the speaker again.
Thank you very much.